Welcome everybody for today's webinar about the new features and performance improvements in Gurobi 9.0. So let's get started. You see the overview of today's webinar presentation. So we start with a short look at performance improvements, and then we dive deep into the new major features. Okay, let's look at the performance improvements first. As usual, we work on performance very hard because that's the main feature that most of our users need to see getting improvement for. And as usual, also with Gurobi 9.0, we have some performance improvements in the code. A brief overview is this one for the LP performance. So for the linear programming part, the default settings, which is concurrent LP, got 7% faster on average on our test set. You have to note that we are using computers with just 4 cores. So that means concurrent LP here is using 1 thread for dual and 3 threads for barrier. If you have more than 4 cores on your machine, then maybe your speed up could be a little bit better than those 7%. The simplex algorithm got faster as well, at least the primal one. Unfortunately, the dual simplex did not see much performance change, but we worked on the linear system solves where we improved the numerics, in particular for warm starts and for several corner cases. The barrier algorithm in total got 7% faster. One of the pieces of barrier is actually the crossover code, which is again the simplex. And here the improved numerics come into play very nicely, that the crossover now is faster because the numerical properties of the simplex algorithm have been improved. And additionally, we added support for AVX 512. So if you have such a machine and you are solving models with very expensive factorizations, then you will see another 40% performance boost on your models due to the AVX 512 support. And overall in our whole test set, this gives a 4% performance improvement that comes on top of those 7% that we have. So looking at mixed integer linear programming, we have an improvement of 18% overall on our test set and 26% if you only look at those models that take at least 100 seconds to solve. As usual, the MIP performance comes really from a large number of individual small improvements that just add up. You see here a list of those improvements, and this is not even complete. But I won't go into the details of all those. I just want to point out a few of them. So we have 2 new types of cutting planes that I want to point out. These RLT cuts and the MIQP cuts. We will come to them later when we talk about the non-convex quadratically constrained programming feature that we have, because those cuts originally come from this domain, but you can also apply them for MILP. So then I want to point out that we have reduced the wait time and parallel synchronization by being more flexible with the workload distribution. So that means that each thread does not need to wait so long anymore in order to find useful work to do. As I said, our machines only have 4 cores. So this means that if you have a machine with a larger number of cores, then probably the speed up that you will see against earlier Gurobi versions is a little bit better than this, at least if you are solving models that have large trees where the synchronization is essential. And then finally, I want to point out one new heuristic that we added. This is a new solution improvement heuristic. This one does not affect the default solves for time to optimality because it is only active when you set a certain set of parameters. And these are the improve start gap, improve start nodes, and improve start time parameters. So consider the case where you only have, for example, 1 hour of time that you can spend on solving your model, and you are not able to solve your model to optimality within this 1 hour, then you are probably interested in finding an as good solution as possible within this 1 hour time frame. So what you would probably do is to say that you just solve like 50 minutes in the regular mode, and in the last 10 minutes of your solve, you would really try to focus on improving the primal bound. And to do so, you would set the improve start time parameter to 50 minutes. And then after these 50 minutes, this improvement heuristic kicks in. And this is the one that we have significantly improved by adding a new component to it. And when we tested that on our own set of models that are too hard to solve to optimality, then we can see that for 83% of those models, this new scheme that we added finds better solutions than the old scheme that we had in version 8.1. Okay, let's look at the last class of problem instances, which we typically measure performance for, which is the mixed integer quadratic programs. That means you have a linear constraints and the quadratic objective function, and then the mixed integer quadratically constrained programs, which means that you have also quadratic constraints, and you may have also a quadratic objective function or a linear function. So MIQPs got 24% faster. Of course, all of those MILP improvements apply as well here. Then we added one more trick that helps quite significantly for so-called pure box QPs, but those are probably not that relevant for practical applications. Then for the MIQCP, so which with quadratic constraints, they got 6% faster. Again, the MILP improvements apply here. And then we also improved our heuristics so that now many of the already existing heuristics for MILP now also work for models with quadratic constraints. And that improves performance for proving optimality, usually only a little bit, but you will probably see a better behavior in terms of finding good feasible solutions earlier if you are solving MIQCPs with Gurobi 9.0. Okay, now coming to the major features that we added, and Gurobi 9.0 is actually a feature release with lots of new features. So one of the main things that we added to Gurobi 9.0 is a step towards nonlinear optimization. So here we have these two main features that play into this, which are the support for bilinear constraints, which then means general non-convex MIQCPs can be solved, and the support for piecewise-linear constraints. So let's start with the bilinear ones. So non-convex quadratic programs, so non-convex quadratic constraints or non-convex quadratic objectives, come in very handy when you want to solve certain types of applications, and they appear in several industries. So one of the most important one is the so-called pooling problem, which appears in the petrochemical industry, but there are other industries as well that need to solve those non-convex quadratic programs, as you see here in this list. So what does non-convexity mean and convexity? So you see here these two pictures. On the left-hand side, a convex constraint. So the blue shaded area, that is the region of feasible solutions. On the right-hand side, that is a non-convex feasible area. So the only difference is the sign of the x square here in this constraint. And when you have a quadratic constraint, so how do you decide whether this is convex or not? So one criterion that makes a quadratic constraint convex is that the Q matrix is positive semi-definite. So in this constraint X transpose QX smaller or equal to B, if the Q matrix is positive semi-definite, then this constraint is convex. So positive semi-definiteness means that for any vector X that you plug into this constraint, so X transpose QX, then this product is non-negative. But there are also other cases where the constraint is convex, but the Q matrix is not positive semi-definite. So the most important case here is the case of second order cones. When you look at this constraint here, so sum over xi square minus z square is smaller or equal to 0, this defines also a convex area as long as the z variable is non-negative. So if you also allow for negative z's, then this cone shape that you see here in the top, bottom left would be extended towards the bottom, and then the area would no longer be convex. But if the z is non-negative, then this is convex, and this can also be solved by prior Gurobi versions. So all Gurobi versions since version 5, I think, would be able to solve such problems with these convex quadratic constraints. But what about non-convex quadratic constraints or objectives? Gurobi 8.1 and earlier versions might still be able to solve those, but only if during pre-solve it is possible to convexify those or to linearize them. So for example, if you have products with at least one of the two variables being binary, then you can linearize them, and then Gurobi 8.1 and earlier versions were able to solve them. But if this is not the case, so if there is a non-convex quadratic constraint that cannot be linearized or convexified, then Gurobi 8.1 would return you an error code, either this GRB error Q not PSD error or the GRB error QCP quality constraint. Now Gurobi 9.0 can just solve those models, independent of whether the constraints or objectives are convex or not. The only thing that you need to do is to set this non-convex parameter to the value 2. So, and what will it do then? The first step is the regular pre-solve will run, and if it finds out that there is a non-convex quadratic constraint or objective, then it would convert them into a set of bilinear constraints and linear constraints. So take this one here as an example. This is a quadratic equality constraint. So quadratic equality constraints are always non-convex. So we would take each of those product terms here and create a new auxiliary variable for it to catch these product terms. So for example, P11 should be equal to x1 squared, and P12 should be equal to x1 times x2. And now using those auxiliary variables, the original non-convex quadratic constraint just translates into a linear constraint in those new variables. But of course, we still have those, in this case, 6 bilinear constraints, and those are still non-convex quadratic constraints. So somehow we need to deal with them. And this is what Gurobi 9.0 can do. We have extended the algorithms in the tree search to be able to deal with these bilinear constraints. And this is done via cutting planes and spatial branching. So spatial branching means to be able to branch on continuous variables. Okay, how is this done? So more generally, our bilinear constraints are a linear term, so a vector A times a variable vector Z, and then plus a single product term. So a coefficient D times a variable X times a variable Y. And that should be smaller or equal to a right-hand side B. So first consider the square case. So that means X and Y are actually the same variable. So we have X squared here. And let's look again at these two cases, the convex one and the non-convex one. And for the convex version, that is easy. So and this, as I said, can already be done by earlier Gurobi versions. So what you do is you come up with a linear relaxation and then add cutting planes to get closer to the quadratic parabola here. So for example, we could start with these 3 linear constraints. That is an outer approximation of the feasible region. And then we call the simplex algorithm to find an optimal solution to this problem. That might be this one here. And then of course, this one is not feasible for the actual problem because it's not inside the blue region. So we add a cutting plane. In this case, we can just separate a tangent cut. That would be this one, and then call the simplex algorithm again to find a new vertex. That could be this one. And then we iterate this procedure until we have reached a point that is close enough to our feasible region so that we can consider it to be feasible. Now for the non-convex case, that is not possible. For example, we have this particular linear programming relaxation. So this is just a secant here. there is no other linear relaxation available here, because otherwise we would cut off into this feasible region of the problem. And say there are other constraints in the problem that come into play here, that then it could be that an optimal solution to our LP relaxation is somewhere here in the middle for this particular variable. Now, what can you do? You cannot separate a cut to separate this point from the feasible region, at least not a linear cut, because every linear cut that would cut off this point would also cut off feasible points from our constraint. The only thing that you can do here is to branch. So you split the domain of the variable into two parts, and this could be a continuous variable. That is why we need spatial branching. And now with the reduced domain of this variable in the two child nodes, we actually can strengthen the linear relaxation, right? Because now we are no longer cutting off the feasible points from this part of the solution space that we consider in this particular child node. But that means that the relaxation needs to be updated locally. Okay, let's look at the mixed product case. So now we are no longer having x squared, but we're having really x times y in our constraints. And this is now a three-dimensional picture that you see here that I took from a paper from Costa and Liberti. And you see here the saddle object here. That is the feasible space of the equation z is equal to x times y. And if you want to linearize this, then the best outer approximation that you can get, so that means the convex hull of this surface, that is the so-called McCormick relaxation. And you can look at this into two parts. So there is the lower and the upper envelope. So the first two inequalities here are defining the lower envelope that you see on the left-hand side picture, and the bottom two inequalities define the upper envelope that you see on the right-hand side picture. And then you combine those, and that is the LP relaxation of the saddle surface that you see here. Now, one thing to point out is that the coefficients of the inequalities in the McCormick envelopes and the right-hand side values, they depend on the lower and upper bounds of the variables. And because of branching, those lower and upper bounds of the variables can change, and that is actually the reason why we do the spatial branching. And that means that these constraints need to be updated in the local child node. So that is something new that you don't have in regular MILP or convex MIQCP solves. So we need to be able to update the coefficients of the constraints given the local bounds of the variables. And this is something that we have implemented in what we call adaptive constraints. So an alternative to that would be to add the constraints, the tighter constraints, as locally valid cuts. But this is not what we do. We really change the coefficients of the existing constraints in the linear programming relaxation. Okay, so and then as a summary, the algorithmic ingredients that we need for being able to solve non-convex MIQCPs to global optimality are that in pre-solve we translate a general non-convex Q constraints into bilinear constraints. Then we add the McCormick relaxation to have an LP relaxation of those constraints. Then we need to be able to branch on continuous variables. So that is the so-called spatial branching. Then we have these adaptive constraints to change the coefficients locally. And if you want to have good performance, then you also need special cutting planes for those. And these are in particular the two cuts that I already mentioned in the beginning, the RLT cuts and the BQP cuts, which stand for RLT's reformulation linearization technique, and the BQP comes from the Boolean quadratic polytope. Those we have already implemented. There's a third type of cuts that are very interesting for this, which come from semi-definite programming. These are the SDP cuts. They are not yet in Gurobi, but we are working on them, so hopefully they will get into the next version of Gurobi. But of course, there are many other cutting planes. So this is a nice way of improving performance to work here on cutting planes. One thing that I have already said, and I want to point out again, is that these cuts that use those product terms can also be used for MILPs, even though you would think that in an MILP there are no products because everything is linear. But if in your original problem you have products that involve binary variables, then these products can be linearized. And often people would do this and present already a linear model to the solver, which actually models also products with binary variables. And now we can reverse engineer this linearization. So that means we detect this modeling of products in the total full model so that we can identify that there is a variable, say z, that is equal to the product of some other variable x and some other variable y. And then we can use this product detection in order to separate RLT cuts and MIQP cuts. And this is one part of the speed up for MILP that we have achieved for Gurobi 9.0. So let's look at performance of our non-convex MIQCP solvers. So Professor Hans Middelmann from the Arizona State University already ran Gurobi 9.0 on a set of quadratically constrained programming problems, which come from the QP lib. Many of them are non-convex. And he also did so with other solvers that are able to solve non-convex problems. And the result here in this very preliminary runs is that Gurobi seems to be faster than the other solvers, and it seems to be able to solve more models within the specified time limit. But you really have to note that those results are really preliminary. So already for MILPs, numerical issues can play a role, but for non-convex MIQCPs, this is much more severe. So it really can happen that two solvers just tell you a different optimal objective value. So this points out that there is something not right, and solvers may have a different interpretation of what feasible is and what not. So those results are really just preliminary, and one would need to really look into much more into the details of the solver's answers to really check whether they are correct or not. And there are also some wrong answers for Gurobi, clearly. And as an additional comment, you have to say that most of the other solvers that are in this list, they are actually able to solve a much larger class of problems, which are general mixed integer nonlinear programming problems. So they are not specialized to non-convex MIQCP, and for this reason, it's a little bit unfair to compare the performance of Gurobi, which can only solve non-convex MIQCPs, to the other solvers which can solve a larger class of problems. Okay, so that was the bilinear part. Then we have added another piece of API to support nonlinear optimization, which is the piecewise-linear constraints. So a piecewise-linear constraint here, and this is just in a single variable, is a constraint where the variable y is equal to a piecewise-linear function that is expressed in a variable x. So the piecewise-linear function is defined by a set of supporting points, and this is what you as a user need to provide to Gurobi, this list of x, y tuples. And then the function between each pair of supporting points is just a linear interpolation between the 2 points. So I'd like to point out that Gurobi supports jumps in this function. So this piecewise-linear function does not necessarily be continuous. It can have such a jump if two consecutive xy tuples have the same x value but a different y value, then this defines a jump in the function. And Gurobi can also deal with an infinite domain of the x variable. So if x goes to infinity, then we just assume that the slope of the function is just identical to the slope of the last piece that has been specified by the tuples. So let's take a look at an example of what you can do with this. So a prime example is that you want to approximate a general nonlinear function with a piecewise linear constraint. So say you have this function y is equal to e to the power of x, with x being between 0 and 1. Then you can approximate this as a piecewise linear constraint. And for example, you may want to take 100 pieces. That would already be a pretty precise approximation. So that means you need 101 points. So the first point being at x equals 0, and the last point being at x equals 1. And in Python, you could write it as follows. So you create these two arrays, xpts and ypts, that specify the tuples. So the first one is for the x coordinate, and the second one is for the y coordinate. Then, as usual, you create a Gurobi model, add the two variables, x and y, and then you add this piecewise linear constraint with this new function at gen construct pwl. You specify the variables x and y. You specify the points x PTS and y PTS, and then you can also give a name to this constraint. Then I also added here an objective function that makes this a little bit more interesting, and then you call optimize. And then here on this slide, you see how this looks like. So this red curve here is the exponent function, and the green line, those are all points that have the same objective value, in this case 0.6, and your goal is to drive the objective to the lower right? Because you have a negative objective coefficient for x and a positive coefficient for y. So if you plug this into Gurobi, so the optimize call will give you this output here. It is actually solved directly at the root node, so that is not very difficult, this problem. And then the optimal solution is x being equal to 0.69 and y being equal to 1.9937. And as you can see here in the picture, that is also the correct solution of this problem. So now on top of this piecewise linear constraints, we have added an API that allows you to explicitly state certain nonlinear functions in a single variable. So we support polynomials, logarithms, exponents, and then sine, cosine, and tangent. So this is yet another type of general constraint, just like the piecewise linear constraints. And as an example, we look again at the exponent function. So we have again y is equal to e to the power of x that we want to model, with x being between 0 and 1. So that we have already done in the previous slides, but you can also do it with this exponent function directly. So you just call the @gen construct exp function given the x and the y, and then you can specify a name for this constraint, and then Gurobi will perform the piecewise linear translation automatically. So of course, what you also need to specify, and you can do so by means of attributes or parameters, is how the piecewise linear translation should be done. So in the previous example, you have 100 pieces. So this is something that you can specify through attributes or parameters. But then using these function constraints might be beneficial to you, because Gurobi is relatively clever inside of the translation, because there are several things that Gurobi can do which you as a user may not be able to do so well. So the first thing is the periodic function sine, cosine, and tangent. Of course, this is something that you can do yourself as well. So it's clear that you want to not linearize all of those individual pieces of the periodic functions individually, but you only want to have one period that you want to translate into a piecewise linear constraint, and then map all other values of the x domain into this single period. That makes the translation work better with a fewer number of pieces. But then something that you may not be able to do so well outside of Gurobi is to exploit pre-solve reductions that may tighten the domains of the involved variables. So during pre-solve, Gurobi can still use these functions as they are. So the domain reductions and the domain propagations would actually use the knowledge that that is an exponent function. And that can be propagated better than a corresponding piecewise linear approximation of that. And only at a certain point, the functional constraints here get translated into piecewise linear constraints. And at that point, it could be that the domains of the variables have already been tightened so that the piecewise linear approximation might be able to use a fewer number of pieces or might be able to achieve a higher accuracy. So that is an advantage of using those function constraints instead of doing your piecewise linear approximation yourself. Okay, so let's take a closer look at the individual options that you can set in order to control how the piecewise linear approximation is being done. So there are 4 attributes here: func pieces, func piece length, func piece error, and func piece ratio that you can specify individually for each piecewise linear function constraint. And if you don't specify them for a particular function constraint, then there are also parameters that then act as the default values, which you can set. And these 4 attributes and parameters control this speed versus accuracy trade-off that you have here. So right, if you use more pieces, then the approximation is more accurate. But of course, more pieces also means more constraints and more variables, and that makes the solve usually slower. And then there is also another thing that you need to consider, which is how the approximation should be done, which is independent of the number of pieces that you use. So you could say that you want to have an underestimation or an overestimation or anything in between, so any convex combination of the two. So take this example on the right-hand side where we have y is equal to x squared. If you select that you want to have an underestimation, then you would get the supporting points PL1, PL2, and PL3. So as you can see in the picture, this piecewise linear function is always below the actual nonlinear function. If you specify that you want to have an overestimation, then you would get the supporting points PU1, PU2, and PU3, which is always above the nonlinear function. And if you set the func piece ratio value to, for example, 0.5, then you would get a piecewise linear constraint that is exactly in the middle between those 2 extreme cases. For these 2 cases here in this example, you have a maximum error of 0.25 in each of the 2 pieces, and that is actually pretty large. So in this particular example, you would probably want to specify to use more pieces than just 2. So having these 2 components, so support for bilinear functions and support for piecewise linear constraints, you are actually able to model very complex nonlinear constraints, at least in theory. So take this as an example here. So you have your constraint z is equal to x to the power of 4 times y to the power of 2. Then you would just need to introduce auxiliary variables. So let u being equal to x squared, v being equal to u squared. So that means v is actually equal to x to the power of 4. And then w being equal to y squared. These are 3 bilinear constraints. And then you add a 4th bilinear constraint that says z is equal to v times w. And using this, you have actually modeled that z is equal to x to the power of 4 times y to the power of 2. And then if you add piecewise linear constraints into the mix, which can approximate single variable nonlinear functions, then you can actually model complex stuff like this one here. Z is equal to sine of x squared times y times e to the power of x plus y squared. This is now possible. Question is, can you solve it? And the reality is that such constraints, as in this example, are probably way too complicated to be solved in a reasonable way. The issue here is that in practice, when you decompose a more complex function into individual bilinear and piecewise linear constraints, then at each step in the decomposition, you will get some error, and these errors will amplify with a more complex decomposition and combination. And then particularly for the piecewise linear approximation, you really have to keep in mind that what the solver will then actually solve is just the piecewise linear approximated problem. It will not solve for the actual nonlinear program. And that could lead to surprising results if your piecewise linear approximation is not fine-grained enough. So take this one here as an example. We have again this function y is equal to x squared, and approximate this with a piecewise linear function. We have chosen the upper approximation through the points pu1, pu2, and pu3. And then in addition, we have a simple linear constraint, in this case y is equal to x minus 0.25, which you see here on the right-hand side in the picture that goes through the points PL1, P, and PL2. And this nonlinear program has a feasible solution in the point P. P is equal to 0.5 and 0.25. But if you use this piecewise linear approximation that is depicted here, then you will find that this piecewise linear approximated program is infeasible, right? Because the linear constraint and the piecewise linear constraint that we use do not have any point in common. And so, in this case, Gurobi will tell you that your problem is infeasible, even though the problem that you have stated with these quadratic function is actually feasible. So that is something that you have to keep in mind when you work with piecewise linear approximations. So in this case, the issue is that the piecewise linear approximation was just not accurate enough. So the error that the piecewise linear approximation has compared to the actual nonlinear function is just too big. Okay, that was nonlinear. Now we come to another nice major new feature, which goes a little bit into the direction of dealing with uncertainty. And this is something that we call MIP Scenario Analysis, or you can also call it what-if analysis or MIP sensitivity analysis. So what is this? So the motivation for this is that a math model is usually just an approximation for some real-world application. The inputs for the model are often just approximations or just forecasted demands, for example. That means also that the business conditions or the environment may change over time. And so for a practitioner, it is often important to know what is this sensitivity of the computed solutions with respect to changes to the model. So one question that a practitioner could ask could be, what would happen if the demand for this particular item is not 10, but is actually 12? Is my solution that I computed still feasible? Is it still optimal? Or how would a different optimal solution to this new problem look like compared to my old solution? So this question can be answered relatively easily if the problem is just an LP, because there you have reduced costs and duals, and those allow you to tell you how sensitive the optimal solution that you have is in terms of model modifications. For integer programs, unfortunately, this does not work. So some people still use it, but that is actually a wrong approach. So what they would do is they would fix all the integer variables to their current value. And then, of course, the remaining problem is just an LP that you can solve. And then this fixed LP has reduced costs and duals. And then you could think that you can just interpret the reduced costs and the duals of this fixed LP just like that you are used from your LP theory and think that this is some meaningful result for the integer program as well. But this is really not the case because it does not consider that you could change your integer variables. So from a mathematical point of view, this approach does not make sense. So for this reason, we have added this MIP scenario analysis, which is much more difficult to do than just fixing variables and solving one LP. So here our approach is the following. We have a base model, and then you specify a set of scenarios, and each scenario is specified as a delta to this base model. So you say for each scenario, what is the difference to the base model? And currently what you can specify are differences in linear objective coefficients, in the variable bounds, and in the right-hand sides of linear constraints. So for example, this demand of 10 could be a right-hand side of a flow conservation constraint in your model. And then you can say that in your scenario number 1, the right-hand side of this constraint is 10, and in scenario number 2, the right-hand side of this constraint is 12. Okay, and then when you have specified all those changes, so all those scenarios, then you call optimize, and then Gurobi will find optimal solutions for each of these scenarios. And you can then look at those solutions, and these solutions may provide the insight into how the solution would change in the different scenarios. Of course, you could already do so with prior versions to Gurobi 9.0, because there's nothing that prevents you from just solving each of those scenarios as an independent MIP. And actually, we had an example, sensitivity.py, and this is also available for other programming languages, which did exactly that. It would solve a mixed integer program and then look at the solution, and then for each binary variable in the problem, it would then solve another MIP where this particular binary variable is fixed to the opposite value compared to the optimal solution of the original MIP. And then you would do this for every binary variable, and then you can say what would happen if I fix this variable to the other side. So the new approach in Gurobi is different from that. First, the API changes makes it more convenient to just define those scenarios via these attributes. And then we have an algorithm that can deal with all those scenarios in a single shot. And this should be faster than solving those MIPs individually. So in future versions, we may even be able to come up with a distributed version of that that's using Compute Server. This is not Gurobi 9.0. This might come in the future. But the most important aspect I want to point out is the last one here. Not that it is faster, the algorithm, but it is also more useful for you if you stop the algorithm early. So for example, due to a time limit. Namely, if this happens, then with this new algorithm that considers all scenarios at once, you usually will have some reasonable information for each scenario. So objective bounds and also feasible solutions. While if you would solve the MIPs individually, one by one, and then stop at some point, then you would have nothing for all of those cases that you did not yet consider within your time limit. So then let me make a few words about more general uncertainty dealing. So just to point it out, of course, uncertainty is something that has been well studied in the past in the academics world, or also in the practical world. The two main concepts that are usually used to deal with uncertainty are stochastic optimization and robust optimization. But this is different from what we do. So what we do is actually much more simple than that. So both stochastic optimization and robust optimization, they want to just find a single solution that is optimal in a certain sense. So in stochastic optimization, you want to find some optimal solution with respect to the expected value over all of the scenarios. And in robust optimization, you want to find a solution that is optimal in a kind of a worst case setting. And you also specify your problems in a slightly different way. In our case, we really find optimal solutions for each of the individual scenarios, which is much simpler than stochastic or robust. Okay, now we come to another set of new features. So while these first 4 bullet points are extensions of what you can do with Gurobi. The last three ones that I want to mention are extensions of how you can do that, how you can access Gurobi. And the first one, that is an extension to our Python API, GurobiPy, which is the support for SciPy sparse matrices and NumPy ND arrays. That is particularly relevant for data scientists and engineers who are usually used to work with matrices instead of individual constraints. So Python itself is a very popular programming language that comes with a huge library of standard components and third-party packages. It has a simple package manager, so it is really simple to install new packages into your Python distribution. And it is a top language for data science. As I said, many data scientists are used to work with matrices, and two of the most well-known packages and most used packages are NumPy and SciPy. So now we decided that it is time for being a little bit more user-friendly to those users that use NumPy and SciPy. Now GurobiPy accepts NumPy's ND arrays and SciPy sparse matrices as input. So that makes it more convenient for you if your underlying model is naturally expressed with matrices. And if this is the case, then using this new GurobiPy interface to matrices is also a little bit faster, because you no longer need to create those intermediate modeling objects for individual linear expressions. So this API comes in two layers. First one is you could add your matrix constraints directly from the data through the new function called addMconstrs. So there you just specify a SciPy sparse matrix A, then a Gurobi variable vector X and the sense vector B and the right-hand side vector B. That would immediately produce the corresponding number of constraints. So each row of the matrix A gives then one constraint. And then the second possibility is you use the overloaded add operator to specify a linear system. So here in this case, you would create your variable X as a matrix variable with a certain shape. So of course, because that is a variable vector, the shape should have just one column, but a larger number of rows. And then you add the constraints through the regular addConstr method, but you use this add operator to specify the matrix vector product. So A add X just means matrix A times vector X, and that should be smaller or equal to B. And B, of course, is also a vector that has the same number of rows as the matrix A and the variable vector X. Let's look at a tiny example to illustrate the syntax here. So on the left-hand side, you have the so to say old algebraic syntax that has been supported since the beginning of Gurobi. You create variables with the addVar call, so your X, Y, Z variables. Then you set an objective where you put in a linear expression that is created with the overloaded plus and star operators here. And then you add constraints one by one in the same way. And then you optimize. On the right-hand side, you have really the same problem in terms of matrix expressions. So first one is you would import NumPy and SciPy sparse. Then you add three variables in a single call with this addMvar function. The shape is 3, that means 3 rows and 1 column. All of those variables should be binary. And then you create a NumPy array with the coefficients of the objective function and use the add operator to specify the scalar product between the object vector and the X variable vector. That is your objective. And then in the next block of code, you see here that you set up a SciPy sparse matrix. Again, the data of the SciPy sparse matrix being NumPy arrays in this case. And then you take this sparse matrix A and a right-hand side vector as a NumPy array RHS and plug it into this addConstr method, again, using the add operator. So the last set of features I want to talk about is dealing with the compute server. So we have greatly extended our compute server offering and added a new component that we call the cluster manager. And that is particularly helpful for corporate IT, and that is a step towards being able to use a private cloud. So what is the cluster manager? The cluster manager is used to administer a cluster of Gurobi Compute Servers. So this cluster of Gurobi Compute Servers may consist of only a single Gurobi Compute Server, that's fine, but there can also be many Gurobi Compute Servers in the same cluster. So using this tool, the cluster manager, the IT department can control and track the size of the cluster and the workload, and also users of this cluster can monitor and manage their jobs. The cluster manager comes with a user management, so you will then have a name and a password to log into the cluster manager, and then the cluster administrators can specify which roles each user has. It could be a regular user, or it could be an admin or a cluster admin. There's also a way to access the cluster manager programmatically, so your client application can use an API key to talk to the cluster manager. We have added a nice web user interface for these on-premise installations, which looks similar to what we already have in the Gurobi Instant Cloud, but now you can use the same thing for your on-premise private cloud installation. So that is a user-friendly graphical interface for both administrators and for users. In particular, in this web UI, you have a job history that tells you about your jobs, gives statistics and logs for the individual jobs that you have launched. And then from a functionality point of view, we have added so-called batch mode support to the cluster manager. That means you can now do offline optimization if you have long-running jobs. So that means the client application can specify the model and launch the job, and then it can disconnect. And later it can reconnect to the cluster manager and retrieve the results. So this is how the web UI looks like. And this particular page here is for such batch jobs. You see that here was a user called Gu who submitted several batch jobs. All of them have already been done, so solved to optimality. It seems that Gu was a little strange here because he submitted 3 times the same problem and then 2 times again the same problem. Why would he do so? Well, of course, this was just for testing our own installation of the cluster manager. And then for the selected job in the bottom part of the screen, you see various information about the job, and there are other tabs that you could click on to show you more information about this particular job. And you could also click on this log button there, and then it would show you the Gurobi solve log of this job. So let's come to batch optimization. So why did we do this? So the compute server itself allows the client code to offload computing work to a server. So for example, it would be useful if the server has much more computing power, much more memory and so forth, so that you would put your hard models onto the server to be able to solve them and then get the solution to your client. But even if you have a very powerful server, a mixed integer program solve can often take very long time. And in prior versions, that required the client code to wait until the server comes back and gives you the solution. This may not be that convenient. So there has been many feature requests from our users who want to be able to disconnect from the compute server and, for example, on a Friday evening, shut down their application, and then on a Monday morning, reconnect to the compute server and check whether the solve has been finished, and if so, retrieve the results. This feature poses some technical problem to us because when you shut down your client application, then all of those modeling objects, like the model itself, the variables, and the constraints, they are gone. Right? You only have this model as represented in the compute server, which is not the same as what the client application had. So this, when you want to then reconnect to the server, this creates a mapping problem. So our solution to this is that if you use the batch mode, then the models are created locally on the client side. And in particular, this means that when you start building a batch model, the only thing that you need is a cluster manager that tells you that you have a valid license. But it could be that all of your compute servers are currently busy. So without batch, you would need to wait for some compute server to be available. If you use batch, you don't need a compute server that is available because the model building happens on the client side. So you can already create your model there. And then what you also should do is you should tag the variables and constraints that are relevant later when you query the solution. So in many cases, you won't need all of the solution values for all of the variables. You only need a subset of the variables that are interesting to you. And that is, tagging is a way to mark those variables and tell the compute server that in its database, it only needs to store these solution values. This helps to save memory in the database. And then after doing that, you submit the model to the compute server, get a batch ID, and then you disconnect. And using this batch ID, you can then later reconnect to the compute server, query the status, and if the compute server tells you that the job has been done, then you can query the solution, and that is then presented to you in a JSON format that you can easily parse. Okay, that was the overview of most of the major Gurobi 9.0 features. There are a number of other improvements that we don't have time to talk about today, but there will be additional webinars in the future that have a deeper dive into many of those new features